Hi, hello there. Welcome to Designing Remote Connectivity. This video discusses the WAN function that provides access to remote sites and the outside world. It details WAN technologies and WAN design considerations. The video explores how these technologies were used, including for remote access with virtual private networks or VPN for backup, and how the internet is used as a backup WAN. This video describes the Enterprise WAN and the Metropolitan Area or MAN architecture, and the Enterprise Branch and Teleworker architectures. The selection of WAN hardware and software components is also discussed. Now for the topic outline of this video lecture, Designing Remote Connectivity, this video will cover identifying WAN technology considerations, designing the Enterprise WAN, and designing the Enterprise Branch. At the end of this video lecture, we are going to summarize designing remote connectivity. Let's get started. Identifying WAN technology considerations. Enterprise Edge WAN technologies. So this section introduces the concept of the wide area networks or WAN, beginning with the definition of WAN and the types of WAN interconnections. Various WAN technologies are described. The section concludes with a discussion of WAN pricing and contract considerations. Designing a WAN is a challenging task. The first design step is to understand the WAN's networking requirements, which are driven by two primary goals. First, you've got the service level agreement or the SLAs. Networks carry application information between computers. If the applications are not applicable to network users, the network fails to achieve its design objectives. Organizations need to define the level of service such as bandwidth, allowed latency, packet loss, and so forth. That is acceptable for the applications running across the WAN. The second one is the cost of investment and usage. WAN designs are always subject to budget limitations. Selecting the right type of WAN technology is critical to providing a reliable services for end-user applications in a cost-effective and efficient manner. Now, flowing from these goals are the following objectives for an effective WAN design. So a well-designed WAN must reflect the goals, characteristics, and policies of an organization. The selected WAN technology should be sufficient for the current and, to some extent, future application requirements. The associated costs of investment and usage should stay within the budget limits. WAN interconnections. Now, this figure here illustrates a three-way that WAN technologies connect the enterprise edge modules with the outside world, represented by the service provider network. So typically, the intent is to provide the following connections. So connectivity between the enterprise edge modules and the internet service provider edge or the ISP edge modules. So connectivity between the enterprise sites across the ISP network, connectivity between the enterprise sites across the service provider or public switch telephone network or PSTN carrier network. So WAN connections can be a point-to-point between two locations or connections to a multi-point. So one service offering such as the old frame relay or the multi-protocol label switching or MPLS network. One of the main issues in WAN connections is selecting the appropriate physical WAN technology. Now, what are the WAN transport technologies? The table here compares various WAN technologies based on the main factors that influence technology selection. So this table provides typical baseline characteristics to help you compare the performance and features offered by different technologies. So often, the offerings of the service provider limit your technology decisions. You can go ahead and search for these technologies on the internet. Example of ADSL implementation. An ADSL circuit connects an ADSL modem on each end of a twisted pair telephone line. This creates three information channels. So you've got the medium speed downstream channel, the low speed upstream channel, and of course the basic telephone service channel. So filters or splitters split off the basic telephone service channel from the digital modem, guaranteeing an uninterrupted basic telephone service even if ADSL fails. Now I have here an example of data over or data and voice over cable. So this figure illustrates some of the components used to transmit data and voice on a cable network. So the Universal Broadband Router, or the UBR, also referred to as the Cable Modem Termination System, or the CMTS, provides high-speed data connectivity and is deployed at the cable company's head end. So the UBR forwards data streams to connect with either the PSTN or the internet. So the cable modem, also referred to as a cable access router at the customer location, offers support for transmission of voice, modem, and fax calls over the TCP/IP cable network. Example of the three uses of wireless. Now, common examples of wireless equipment include cellular phones, global positioning systems, cordless computer peripherals, satellite televisions, and wireless LANs or WLANs. So as shown in this figure here, wireless implementations includes bridge wireless, cellular wireless, and wireless LANs. Now for the bridge wireless, this is designed to connect two or more networks, typically located in different buildings, at a high data rates for data-intensive line-of-sight applications. A series of wireless bridges or routers connect discrete distance sites into a single LAN, interconnecting hard-to-wire sites, non-contiguous floors, satellite offices, school or corporate campus settings, temporary networks, and warehouses. Next would be the mobile wireless. So this includes cellular voice and data applications. Wireless technology usage increased with the introduction of digital services on wireless. Second and third generation mobile phones offer better connectivity and higher speeds. So mobile wireless technologies includes the following. You've got the GPS, okay, the Global System for Mobile or GSM, the General Packet Radio Service or GPRS, the Universal Mobile Telephone Service or UMTS, the Code Division Multiple Access or the CDMA, and other technologies. Next would be the wireless LAN. So developed because of demand for LAN connections over the air and often used for intra-building communications. So WLAN technology can replace a traditional wired network or extend its reach and capabilities. WLANs cover a growing range of applications such as guest access and voice, and support services such as advanced security and location of wireless devices. Synchronous optical network and synchronous digital hierarchy. So SONET, or the synchronous optical network, okay, and you've got the SDH, or the synchronous digital hierarchy. This is a circuit-based bandwidth efficient technology. So SONET SDH establishes a high-speed circuit using TDM frames in ring topologies over an optical infrastructure, as illustrated here in the diagram. So it results in a guaranteed bandwidth regardless of the actual usage. So common bit rates are 155 Mbps and 622 Mbps with a current maximum of 10 Gbps or gigabit per second. Next would be the dense wavelength division multiplexing, or DWDM. So dense wavelength division multiplexing is illustrated on this figure, which increases the bandwidth on optical medium. So DWDM increases the available bandwidth on a single strand of fiber using a multi-channel signaling. DWDM is a crucial component of optical networks. It maximizes the use of installed fiber cable and allows new services to be provisioned efficiently over the existing infrastructure. So flexible add and drop modules allow individual channels to be dropped and inserted along a route. An open architecture system allows the interconnection of a variety of devices, including SONET terminals, ATM switches, and IP routers. DWDM is also used inside a SONET SDH ring. Next would be the dark fiber. So dark fiber refers to fiber optic cables leased from the service provider and connected to a company's own infrastructure. So dark fiber is illustrated on this figure here. So the framing of a dark fiber is provided by a company's devices and does not have to be a SONET or SDH. So as a result, the dark fiber connection eliminates the need for SONET SDH multiplexers, which are required in SONET SDH rings. Each edge device connects directly over the site-to-site dark fiber using a layer 2 encapsulation such as gigabit Ethernet. Now, when such connectivity is used to transmit data over significantly long distances, regenerators or DWDM concentrators are inserted into the link to maintain signal integrity and provide appropriate jitter control. WAN transport technology pricing considerations. So pricing used to include an access circuit and a distance-sensitive rate. So access circuit provisioning generally takes 60 days or more lead time. Now for the technology, like the old frame relay and ATM, pricing includes an access circuit charge. Well, this would definitely depend if the service is provided on your area. So sometimes you've got a per PVC and possibly per bandwidth charges. MPLS VPN pricing is generally comparable with the old frame relays and ATM. So take note that the pricing, time frame, and contract details provided here are examples from the US market. Okay? Now, organizations in other countries might have different experiences. However, the items in this section should be considered when implementing a wide area network. Service and pricing options between carriers should be compared and negotiated depending on competition in the area. Methodology used in the enterprise edge design. So this section describes the WAN design methodology and the application and technical requirements aspects of the WAN design. The different possibilities for WAN ownership are discussed. So WAN bandwidth optimization techniques are described. The methodology espoused here follows the guidelines for the prepare, plan, design, implement, operate, optimize, or the PPDIO methodology introduced in the previous video, applying methodology to a network design. Now, the network designer should follow these steps when planning and designing the enterprise edge based on the PPDIO methodology. So step 1 would be analyzing the customer requirements. The initial setup or the initial step in the design methodology is to analyze the requirements of the network and its users, including the type of applications, the traffic volume, and the traffic patterns. Second would be characterizing the existing network and sites. The second step is to analyze the existing networking infrastructure and sites, including the technology used and the location of hosts, servers, terminals, and other endnodes. Step 3 is designing the network topology and solutions. The final step in the design methodology is to develop the overall network topology and each appropriate services based on the availability of the technology and taking part into the projected traffic patterns, technology performance constraints, and network reliability. Identifying application requirements. So application requirements of a WAN design. So just as application requirements drives the enterprise campus design as illustrated in the previous video, designing basic campus and data center networks, they also affect the enterprise edge WAN design. So application availability is a key user requirement. The chief components of application availability are response time. So throughput, packet loss, okay, and reliability. Now this table here analyzes these components, which are discussed in the following sections. So first, let's discuss the response time. Response time is the time between a user requests, such as the entry of a command or keystroke, and the host system's command execution or response delivery. In data transmission, throughput is the amount of data moved successfully from one place to another in a given time period. In telecommunication transmission, packet loss is expressed as bit error rate or BER, which is the percentage of bits that have errors relative to the total number of bits received in transmission. Reliability, although reliability is always important, some applications have requirements that exceed typical needs. Determining the maximum offered traffic. So technical requirements, maximum offered traffic. So the goal of every WAN design should be to optimize link performance in terms of offered traffic, link utilization, and response time. So to optimize link performance, the designer must balance between end user and network manager requirements, which are usually diametrically opposed. So end users usually require minimum application response times over a WAN link, whereas the network manager's goal is to maximize the link utilization. WAN resources have a finite capacity. So response time problems typically affects only users. For example, it probably does not matter to the network manager if query results are returned 120 milliseconds sooner rather than later. So response time is a thermometer of usability for users. So users perceive data processing experience in terms of how quickly they can get their screen to update. So they view data processing in terms of response time and do not actually care about link utilization. So the graph here illustrates the response time and link utilization relative to offered traffic. So the response time increases when the offered traffic until it reaches an acceptable or an unacceptable point for the end user. So similarly, the link utilization increases with the offered traffic to the point that the link becomes saturated. So the designer's goal is to determine the maximum offered traffic that is acceptable to both the end user and the network manager. Technical requirements, bandwidth. So in a qualitative sense, the required bandwidth is proportional to the data's complexity for a given level of system performance. So for example, downloading a photograph in 1 second takes more bandwidth than downloading a page of text in 1 second. So large sound files, computer programs, and animated videos require even more bandwidth for acceptable system performance. So one of the main issues involved in WAN connections is the selection of appropriate technologies that provide sufficient bandwidth. Now this table here illustrates the ranges of bandwidth commonly supported by the given technologies. So bandwidth is inexpensive in the LAN, where connectivity is typically limited only by hardware implementation and ongoing maintenance costs. In WAN, bandwidth has typically been the overriding cost. The delay-sensitive traffic, such as voice, has remained separate from data. However, new applications and the economics of supporting them are forcing these conversions to change. And basically, the ideal choice here is the use of fiber optic. Evaluating the cost effectiveness of WAN ownership. So in the WAN environment, the following usually represented fixed costs. Equipment purchase such as modems, channel device or service unit, data service units, and router interfaces. Circuit and service provisioning, network management tools and platforms. Recurring costs includes the monthly circuit fees from the service providers and the WAN support and maintenance, including any network management center personnel. So from the ownership perspective, WAN links can be thought of the following three categories here: private, leased, and shared. Now for private, a private WAN uses private transmission systems to connect distant LANs. The owner of the private WAN must buy, configure, and maintain the physical layer connectivity such as copper, fiber, wireless, and coaxial, if some of the organization are still using coaxial, and the terminal equipment required to connect locations. Next would be leased. A leased WAN uses dedicated bandwidth from a carrier company with either private or leased terminal equipment. The provider provisions the circuit and provides the maintenance. Last would be shared. A shared WAN shares the physical resources with many users. Carriers offer a variety of circuit or packet switching transport networks such as MPLS and other technologies. Optimizing bandwidth in a WAN. It is expensive to transmit data over WAN. Therefore, one of many different techniques such as data compression, bandwidth combination, tuning the window size, congestion management, queuing and scheduling, congestion avoidance, and traffic shaping and policing can be used to optimize bandwidth usage and improve overall performance. So the following sections describes this technique. So let's start with data compression. So compression is a reduction of data size to save transmission time. Compression enables more efficient use of the available WAN bandwidth, which is often limited and is generally a bottleneck. Compression allows higher throughput because it squeezes packet size and therefore increases the amount of data that can be sent through a transmission resource in a given time period. Okay, so the next one would be bandwidth combination. So PPP is commonly used to establish a direct connection between two devices. PPP is point-to-point protocol. This is a layer 2 protocol for connection over synchronous and asynchronous circuits. So for example, PPP is used when connecting computers using serial cables, phone lines, trunk lines, cellular telephones, specialized radio links, or fiber optic links. An encapsulated form of PPP, which is the PPPoE or PPPoA, is commonly used in a similar role with DSL internet service. So the next one is window size. Window size is the maximum number of frames or amount of data the sender can transmit before it must wait for an acknowledgement. The current window size is defined as the number of frames or amount of data that can be sent at the current time. This is always less than or equal to the window size. So we are going to cover queuing and traffic shaping on the next slides. For the queuing to improve link utilization. So to improve link utilization, Cisco has developed the QoS, or the quality of service techniques, to avoid temporary congestion and to provide preferential treatment of critical applications. So QoS mechanisms such as queuing and scheduling, policing or limiting the access rate, and traffic shaping enables network operators to deploy and operate large-scale networks that efficiently handle both bandwidth-hungry such as multimedia and web traffic, and mission-critical applications such as hosted-based applications. So key types of queuing includes priority queuing, you've got the custom queuing, weighted fair queuing, class-based weighted fair queuing, and low latency queuing. You can go ahead and check the supplementary videos for additional information about queuing. Traffic shaping and policing. Traffic shaping and traffic policing, also referred to as the committed access rate, are similar mechanisms in that both inspect traffic and take action based on various characteristics of that traffic. So these characteristics can be based on whether the traffic is over or under a given rate, or is based on some bits in the IP packet header, such as the DSCP or IP precedence. Now, to summarize identifying WAN technology considerations. So a WAN is a communications network that covers a relatively broad geographic area and carries a variety of traffic using transmission facilities that are typically provided by the service providers or SPs. The multiple WAN transport technologies vary in bandwidth, performance characteristics, and costs. In WAN design, enterprise edge connectivity requirements influence the trade-off between the cost of bandwidth and bandwidth efficiency.